edges. And then it was I mean, the obvious lower bound is that you need a linear number of edges to sparsify. But then it was this huge mystery how you can possibly do better than n log n. Because anything based on random sampling, there's a coupon collector problem where it looks like n log n is the barrier. And this didn't come up just in graph sparsification. It comes up in many, many places. So when they managed to get it down to a linear number of edges, this was pretty amazing. It surprised a lot of people. So now you tell us about it.
Okay. So yeah, so that's what it's going to be about. So, oh wait a minute. Sorry. Okay. Yeah. Okay. So yeah. So in the previous lecture, which hopefully many of you came to, basically there was a definition and there was a theorem. The definition was the definition of spectral approximation of graphs. It's known as physical approximation. And we said that a graph H approximates the graph G up to some factor of kappa if the Laplacian of G is sandwiched between the Laplacian of H and kappa times the Laplacian of H. What this means is the pointwise the quadratic forms are approximated. And the main theorem that I showed you is that while every undirected weighted graph G has a 1 plus epsilon approximation in this sense with n log n over epsilon squared edges. And moreover, there's a very fast algorithm which finds it based on sampling according to effective resistances. And the sort of motivating question, the motivating sort of example for what I'm going to show you here is that recall this first example that I showed you about sparsifying the complete graph, where I took a complete graph and approximated it by union of a constant number of random matchings. Here it turned out that to get a 1 plus epsilon approximation, the right answer is 2 over epsilon squared degree. Okay? And there's no log n here. There's no dependence on the size of the graph. And this is an expander graph. And if there was a log n, then, well, you would no longer consider an expander graph. And there's, there's a qualitative difference between the degree going to infinity and the degree being constant. So this is, this is sort of the issue that I want to address here. So remember that the theorem that we proved last time essentially boiled down to the following theorem about matrices, about decompositions of the identity, that given any vectors vi so that the sum of outer products is equal to the identity, there are some scalars, at most n log n over epsilon squared non-zero, so you get a 1 plus epsilon approximation. And the whole proof was essentially I took a graph, I turned it into a bunch of vectors which had some quadratic form, I applied this theorem, and then I got a sparse set of vectors, and that corresponded to a sparse graph. And this log n is present in this linear algebraic theorem as well, and where it really comes from is this matrix Chernoff bound. This was the main tool that we used from random matrix theory, which says that if you have some ID n by n random matrices whose norms are bounded by some m and the expectation is the identity, then the probability that if you take k samples and average them, that it's epsilon away from the expectation, which is the identity, is 2n times this exponential. And when you plug in n log n over epsilon squared for the number of samples, it shows you that this is the number of samples you need in n dimensions. Okay? And this is really the root of this log n. That it's this random sampling theorem. That if you have something whose expectation is the identity, you need n log n over epsilon squared samples to get epsilon close to the identity. And as James mentioned, this is the n log n we want to remove, but unfortunately this n log n is actually essential. So as James mentioned, there's a tight example which shows that you need n log n samples. And it's very instructive to look at this example. So the example is the matrices are all diagonal. So the random matrix X is a diagonal matrix, which is equal to, this should be n. N times EI transpose the probability 1 over n. Okay? So it's literally just, it's just a matrix that, it's a diagonal matrix, and you just pick some entry randomly and you put an n over there. So that's what it is. Now, if you it's easy to see that the expected matrix here is the identity, because if you average all of those, you just get the identity. But if you take k samples of such a random matrix, that amounts to throwing k balls into n base, because each time I'm picking one of the diagonal entries. And the eigenvalues of a diagonal matrix are just the entries. So if I want this thing to be close to the identity or to some scaling of the identity, I need all the bins to have the same number of balls. And it's well known that you need at least log n over log n. K, you need k to be at least basically n log n for that to hold. if you just pick linearly many samples, some of the bins are going to be empty. So actually this log-in is essential. And in the case of a graph also, if you've thought about random graphs, it's easy to see that any reasonable distribution, like any IID distribution on graphs, like if you just pick random edges, unless you have average degree log-n, you're going to get some isolated vertices. And that's sort of a similar phenomenon. However, what's interesting to note is that in this example, there is an easy way to actually get an approximation of the identity, and that's by a greedy algorithm. So you just get these balls and you just put it in the least occupied bin, right? So if I was able to, if I was able to choose my matrices deterministically, nothing is forcing. I mean, nothing in this problem forces me to use randomness, right? If I could actually just do it greedily, then it's very easy. Then in n samples, I just pick one of each entry and I'm done. So the theorem I'm going to tell you about today is this theorem that we proved with Batson and Spielman, which has the same setup as the previous theorem. You have some vectors, their decomposition of the identity, their moment ellipsoid looks like a sphere like this. Then there are some scalars that 1 plus epsilon approximate the identity, but now the number is 4n over epsilon squared, so there's no log n. Okay? And this is based on a greedy approach. So it's, like in the balls and bins, I'm not going to pick one ball at a time, which amounts to picking one vector at a time, and get rid of this log n. So recall, what we want to do here, right? This is the goal. You're given these vectors, vi's. You have the sphere. You want to generate some scalars Si, this should be I, so that this matrix, which is obtained by just picking some of these vectors and rescaling them, if you look at its eigenvalues, they're between 1 and kappa, which all that means is if you plot the level sets of the quadratic form of this matrix, it's always between 1 and kappa. Okay, so we're going to do this slowly, greedily, and the picture is sort of like this. It's sort of like blowing up a balloon. So I'm going to start off with nothing. So let A denote whatever my current matrix is that I'm trying to build. And in the first step, I'm going to add some vector times some scaling, some SVV transpose from my collection. So I'm going to choose one of my vectors, choose some scaling, and get some, rank 1 matrix. It's going to have one non-zero eigenvalue, or it's going to have a very degenerate ellipsoid. And then in the second step, I'm going to do it again. I'm going to add another scaling of one of my vectors, and now it's going to be a rank 2 matrix. It's going to have two non-zero eigenvalues, and I'm going to keep doing this. So every step that I take here, because I'm adding a positive semi-definite matrix, this matrix is getting bigger. So you think of this ellipsoid as getting bigger. And as you keep going, this thing sort of blows up like a balloon. And in the end, what I would like is that after some order and steps, not too many steps, I've added these vectors in a way that this thing is sort of balanced in all directions. Okay? So, I need at least n steps even to get full rank. And basically, I want to pack all the directions sort of evenly so that the shape of this thing is like a sphere. So that's the analogy with the balls and bins, where I was putting balls in the least occupied bin. Now I somehow want to choose these directions to if this thing is getting flat in some direction, I want to compensate for that. Okay. So the basic phenomenon I need to understand if I'm going to do this, if I'm going to do these rank 1 updates of matrices, is what does a rank 1 update do to the eigenvalues of a matrix? Right? So if I have some matrix and I add one of these guys, two things happen, right? So the eigenvalues change and the eigenvectors also change. So this ellipsoid sort of rotates and its length of its axes change. So I need to understand what happens to these things. So what happens is pretty well understood. So let's say I have some matrix A with real eigenvalues, so a symmetric matrix, and these blue, balls are the eigenvalues. Let's say when I add some matrix VB transpose, a rank 1, this is really important. What ends up happening is that I get a new set of eigenvalues, and all the new eigenvalues are bigger than the old eigenvalues because this is strictly bigger in the positive semi-definite ordering. And they're not just bigger in some arbitrary way. Something very structured happens, which is you get this interlacing phenomenon. So between every two eigenvalues of the old matrix, you have an eigenvalue of the updated matrix. So So they all sort of move forward, but they never jump across. And this is something that was proven by Cauchy in the 1800s. Okay. So since this is really the fundamental structure that I'm going to use to prove this theorem, I'm now going to prove this for you from scratch, and it's sort of a cool thing. And the proof is based on looking at the characteristic. I mean, there are many ways of proving it, actually, but the proof I'm going to show you is based on looking at the characteristic polynomial. So we're used to thinking of eigenvalues as solutions to ax equals lambda x or something like that. Well, there are also roots of this polynomial, determinant of xi minus a, which is a univariate polynomial. So I'm going to denote that by p of a. And this interlacing structure becomes sort of really clear when you analyze what happens to the characteristic polynomial under a rank 1 update. Okay, so this is the first time in my life that I'm going to try to write on the slides, but let's see what happens. Okay, should I just write on the board?
Yeah, let's.
Okay, I'll just write on the board. Sorry. Well, okay, okay, I'm just gonna write on the board. That's fine. But I know how to write on the board anyway, so let's see the other things. Well, that's good. Right.
You have an eraser there.
Yeah, I have an eraser here. Huh? Oh, there's an eraser there. Good. Right. So, okay. So I have some matrix A, and it has some characteristic polynomial P of A. Is this big enough? Now I'm interested in the matrix A plus VV transpose, where V is some vector. And now the nice thing is there's a nice formula for the characteristic polynomial of this rank 1 update. So I write determinant of xi minus A minus VV transpose. This is the characteristic polynomial of A plus VV transpose. Now determinant is a homomorphism, so I can take xi minus A out. So this is equal to determinant of xi minus A times identity minus xi minus A inverse VV transpose. What? I'm sorry, determinant of. Okay. And now this isn't the identity minus a rank 1 matrix. So its eigenvalues are all 1, except it has one eigenvalue which is just basically depends on the norm of this vector. So you can actually write down what this is explicitly. Another way to see it is you can just sort of rearrange things inside the determinant. You get that this is determinant of xi minus A times 1 minus V transpose xi minus A inverse V. Okay, so this fact is often called the matrix determinant lemma. This is literally the proof. And now we'll see that this guy is just the characteristic polynomial of A. And what is this? So I can diagonalize xi minus A inverse. Well, okay, let's just diagonalize A first, right? So A is equal to sum of lambda I ui transpose.
So you were assuming that V is a unit vector.
No, V is any vector. This is true for any vector. V doesn't need to be a vector. Okay. So let's say you diagonalize A like this. It's a symmetric matrix. Then x I minus A inverse is equal to sum of 1 over x minus lambda I ui transpose. So in particular, the quadratic form of this, when I look at V transpose xi minus A inverse V, I get 1 minus the sum of the V transpose these guys, which is nothing but the sum of 1 over x minus lambda I, and then I get V inner product ui squared, where ui are the eigenvectors. Okay. So, so what this is telling me is that the new characteristic polynomial is the old characteristic polynomial times this rational function. Right? Now, this when this is 0, one of these things has to be 0. Okay. So the roots of this new characteristic polynomial are either just the roots of A. So those actually just correspond to the directions in which V inner product ui is equal to 0. So if I add a vector V which is orthogonal to some eigenvector, then the corresponding eigenvalue simply doesn't change. So let's assume that doesn't happen. Let's assume all these inner products are non-zero. Okay. Then the roots of this updated characteristic polynomial are just a set of points x for which this rational function is equal to 0. I'm sorry, this whole thing is equal to 0, which is just a set of points for which the set of points for which the sum of v inner product ui squared divided by x minus lambda I, this is a rational function, is equal to 1, because that's where this whole thing is equal to 0. Is this too low? Yeah, sort of. Okay. So I'll write it over there. Okay, and now I'm just going to show you a picture, right? So I've identified a function whose I've shown you that the roots of this new characteristic polynomial are a certain level set of this rational function. This rational function has n poles, which are just the roots of the old characteristic polynomial. It has n poles at the lambda I. So if the old matrix.
Can you use a darker pen?
Oh yeah, sure. So okay. So if the roots of the of my matrix A are lambda 1, lambda 2, up to lambda n, then I just showed that the roots of A plus VV transpose are the set where this rational function is equal to 1, right? Well, I can just plot this, right? So this has poles at the roots. It looks like basically looks like this. Okay. And well, I'm interested in the level set where this thing is equal to 1. So and now I can just sort of see that these guys interlace the old guys. I mean, you can prove this. It's a continuous function, whatever. So you can prove that each of these guys has exactly one point where it's equal to 1 between every two of the old roots. And multiplicities are not an issue.
So it's crucial that the numerators are positive.
Yes, it's crucial that numerators are positive, and they are because they're squares. Yes, it's very important. So yeah, I mean, this drawing implicitly, yeah, the numerators are positive. So yeah. So by looking at the characteristic polynomial, you identify the roots of the rank 1 update as some level set of this rational function, which then basically is by inspection you see that all the eigenvalues are interlacing. Okay, so this was, I guess it didn't work out. So, right, okay, so are there any questions about this? This is.
What breaks down when the update is not rank 1?
Yeah, what breaks down when the update is not rank 1? Well, I mean, even this fact is no longer true. So here you get a number. When it's rank 2, you get a 2 by 2 determinant here. And then, well, it's also false when it's not rank 1, but yeah.
Yes, was saying which step of the proof?
Yeah, the step of the proof is the first one. So okay, and yeah, okay, and the fact that we use is called matrix determinant. Okay, and yes, the roots of the updated matrix are zeros of this. Now, what I just showed you there's sort of a nice intuitive way to think about it. So I mean, even if, somehow the main content of this talk should be that it's useful to think of eigenvalues as repelling electrical charges. Okay? And that's not something I came up with, it's something Sego described in his book. And it's basically an immediate consequence of the picture that I just drew. Okay? So I'm going to describe a physical model that describes eigenvalues of a matrix and how they behave under rank 1 updates. So here's the physical model. So the real line is a slope. And the eigenvalues are, let's say, unit charge particles sitting on the slope. And at the locations of the eigenvalues, there are these barriers. So there are these things sticking out of the slope. And there's gravity, and these things are just sort of resting against these things that are sticking out. So this is my physical representation of the eigenvalues of the matrix A. Now, what happens when I add this rank 1 update VB transpose? Well, these barriers, I'm now going to put charges on them. I'm going to put positive charges on them, where the amount of charge on the ith barrier is equal to the squared inner product between the vector that I add and the ith eigenvector. All right. And when once I add these charges, the charges on the barriers repel these charged particles, which are the original eigenvalues. So this first eigenvalue originally was resting over here. It's going to get pushed up. So suppose I had a vector which has projection onto the first, second, and nth eigenvector. And I'm going to put charges on these 3 barriers. This guy is going to get pushed up here. It's going to get pushed down by the next one. And it's actually going to get pushed down by this one too, but it's going to be far away. It's not going to make much of a difference. And then this guy is going to get pushed up by these repulsion from all the other barriers. And the law of repulsion is the inverse law. Okay. So the force of repulsion is proportional to the charge on the barrier and inversely proportional to the distance. So in particular, if I add if my vector has some projection on the first eigenvector, then I add some non-zero charge over there. That means the first eigenvalue must move at least a little bit because the repulsion is infinite. Okay, and then I said there's also gravity. These things have mass. So they don't just shoot up off to infinity, they also get pulled down by gravity, and that's what this 1 stands for. So at some point, they reach some equilibrium under all these forces. So there's some upward and downward repulsion, and then there's gravity. And these eigenvalues settle at some place, and this is the location of the new eigenvalues of the matrix, A plus UV transpose. But this is nothing, this is just a story created out of this thing that I wrote here, right? But it's useful to think of them that way, as some kind of repelling particles. So just to get you used to this way of thinking, let me show you some examples. So in the first example, let's say I add a vector which is just a multiple of the first eigenvector. All right. So then what happens is what happens is something that looks like this. This thing has a lot of charge, so it pushes this guy up and it gets stuck here. It pushes this guy up, it gets stuck here. And it pushes this guy up, and it keeps doing this until somebody gets balanced out by gravity. The force of repulsion is decaying as you get further and further, and the equilibrium maybe looks something like this. And yeah, the way to think about it is that things never jump across these barriers. But of course, this is also just a story, because another way of looking at this is that none of the other eigenvalues move, and this guy just shoots forward by whatever the norm of the vector that you added is. And that's okay too. The eigenvalues don't actually have names. So, okay. Here's another example. Suppose I had a vector that has equal charge on the first 2 barriers, so equal projection on the first 2 eigenvectors. Then what happens is something that looks like this, like what I showed you in the first slide. The interesting thing to note here is that no matter how much charge I add to these vectors, this first eigenvalue is still going to stay in that interval because of interlacing, but it's not even going to go very far because it's actually getting some downward repulsion from the second eigenvalue. Okay. So, the thing to take away from this is that even if I add a huge amount of some eigenvector, if it's blocked by the next eigenvector, it's not going to move very far. And instead what's going to happen is that the next one is going to move far. Okay. So maybe you want to think of these as billiard balls or something. I mean, I don't know. I'm just putting, billiard balls are different actually, but it's not. But anyway, so yeah. And then the third example, which is sort of extremely important for us, is if I add a vector which has equal projection onto all the eigenvectors. Okay, so I add a v that's just equal linear combination of all the eigenvectors. Then I add a tiny amount of charge to all these barriers, and what I expect to happen is something like this. So I don't expect anything too crazy to happen because there's no clustering of eigenvalues, so I don't expect anything to shoot off too much. I just expect everybody to move a little bit in their interval. Okay. So I can get more quantitative, so far I've just been like speaking very vaguely, I can get more quantitative information about what exactly happens here by again looking at the characteristic polynomial. So I'm going to call such a vector which has equal amount of weight on all the eigenvectors, so equal amount of charge on all the barriers. I'm going to call it a balanced vector. And something really nice happens when I add a balanced vector, which is, what it does to the characteristic polynomial is extremely clean. So this is the formula that I wrote here, or there. Okay? The new characteristic polynomial is the old one times, x minus lambda x, this should be minus. But now, all these inner products are the same. Let's say they're all equal to 1. Right? So then all these guys just become 1s. So this becomes P of A plus P of A times the sum of, minus the sum of 1 over x minus lambda x. But now, remember that P of A is just, it's a polynomial with roots at lambda x, right? So if I multiply this by this guy, and I just get the derivative of P of A, right? Because I get all the n minus 1 ways product. So when I add a balanced vector, I subtract off the derivative of the polynomial, and the amount of the derivative I subtract is basically the normal of the vector. Okay, so the reason I am belaboring this particular case is that this is related to what happens in our actual situation, right? So remember the setup. So the input, on our problem is these vectors VE, which originally came from edges of a graph, such that the sum of their outer products are equal to the identity. And another way of saying that is that for any eigenvector ui of any matrix, the sum of squared projections is equal to 1. That's what it means for it to be the Cauchy identity, right? The quadratic form is always equal to 1. So what that means is if I pick a random vector from such a collection, and I have some matrix, then the expected squared projection along any of the eigendirections is exactly the same. It's just 1 over m. It's not particularly likely to hit any particular direction because it treats all directions equally, at least as far as marginals go. Alright? So I'm not saying something very strong. I'm just saying that the marginal projection on each eigenvector is 1 over n. I'm not saying there exists a single vector which is actually balanced. I'm just saying that in expectation, the expected amount of charge you put on each one of those guys is the same. Okay, so now I'm going to do something which is sort of just a dream, but let's just do it anyway. So I just told you that when you add this balanced vector, you just subtract off a multiple of the derivative. And then I also told you that adding a random vector has something to do with this, because that's what happens in expectation. So let me see what happens when I keep doing this. And let me keep track of the expected characteristic polynomial of the matrices that I see. Okay, this is sort of a weird thing to do. It's not exactly what I'm interested in, but it's easy to do, so let's just do it. So I'm going to start off with the 0 matrix, so I'm calling A sub 0. And the initial polynomial is just x to the n, so all the roots are 0. So now I know that my vectors that I'm choosing from my collection, the expected inner product squared with any of the eigenvectors of this matrix, which are, it doesn't matter, it's a 0 matrix, is 1 over m. So what that means is that after one step, the expected characteristic polynomial that I see is the original characteristic polynomial minus 1 over m times its derivative. Alright. And if I were to actually look at an actual realization of this process, the eigenvalues might look something like this. Now the matrix has 1 non-zero eigenvalues in the rank 1 matrix. But now I can do this again. Okay. So I can add another vector. In the next step, I can choose another random vector, and I'll get another rank 1 update. But again, if I just look at the expected characteristic polynomial, this corresponds to subtracting off a multiple of the derivative. Okay. And then I do it again. I have this interlacing thing going on, which I just proved. These eigenvalues move forward in some sort of way. I don't really know how to keep track of this realization, this actual instance that I'm seeing, so let me just keep track of the expected characteristic polynomial. That's easy. Every time what happens is you subtract off a multiple of the derivative. And if instead, if you were to follow the roots of this polynomial, right, then these, you might imagine by this physical model that I showed you on the previous slide, these do indeed move forward in some sort of smooth way. Okay. So I'm not making any claims about an actual realization of this random process. I'm saying that if you just keep track of the roots of this expected characteristic polynomial, then what I showed you with this charged particle model should happen. And if you do this forever, then because everything, the intuition was that it was happening steadily, these things should end up clustered together somewhere far away from zero. And then maybe the question is, if you do this for long enough, will it be the case that the ratio of the largest to smallest is bounded by some constant kappa? So the punchline is that this process is a very well studied thing, where you take a polynomial and keep subtracting off the derivative. It generates a polynomials from a classical family of orthogonal polynomials called the Laguerre polynomials. So if you keep doing this, you actually get certain associated Laguerre polynomials. And these are polynomials that are studied in a bunch of different contexts for over 100 years. And a lot of stuff is known about their roots, and their bounds on what the roots are. And in particular, it's known that after 4n over epsilon squared steps, the ratio of the largest to smallest root is 1 plus epsilon. So the rate of convergence of this process is well understood. Okay, so that sounds great. That's exactly what I wanted to prove. But there's a major problem here. The picture that I just showed you is tracking the roots of the expected characteristic polynomial, right? What I'm actually interested in is the expectation of the roots of this random polynomial. So I'm interested in actual honest-to-God vectors that I can get my hands on, not in these weird polynomials that I got by averaging polynomials. And the problem is that the roots of the expectation are in general not equal to the expectation of the roots. So this is not actually a proof, because this doesn't, it's some sort of heuristic exercise, but it's not actually a proof. It doesn't tell you about the existence of any particular root. So this is sort of just a dream. This is all sounded great, but it's a dream. Okay, so nonetheless, the theorem that we prove is if we allow arbitrary scalings of the vectors, so remember we have one more knob to play with, and every step we can choose a vector and a scaling, then there's a greedy algorithm which exactly matches the behavior of this dream, that you actually get this 4n over epsilon squared convergence. And this actual proof is a greedy algorithm which gives the rule for choosing the next vector in a manner which mimics the behavior of these roots of the Laguerre polynomial. And it's greedy, so it's greedy with respect to some potential function. It's greedy with respect to some, like how do I decide what vector to choose next? It's based on, it's based on this phenomenon that eigenvalues are like repelling electrical charges. So basically, this greedy algorithm, what it does is it keeps track of the total repulsion of these charges and uses that to guide the next choice of vector. Okay, so let me.
Sorry.
Yes.
Your dream process has no chance of working, right? Because if it did work, it'd be linear instead of n log n.
Well, no.
It's a random process too, right?
Oh yeah. Well, so what is this dream process, right? So, the dream random process has no chance of working.
Dream random process.
But the expected polynomials that you observe during the dream random process have nice behavior.
Right.
That's all I'm saying. Okay. So nonetheless, anyways, it works out, and this is what we prove. We get exactly the same one. So let me now tell you about how to actually prove this. And for simplicity, I'm going to show you the proof for how to get 6n vectors with a 13-factor approximation. Not not n over epsilon squared vectors with 1 plus epsilon, but all the ideas are there. So the basic picture is something like this. So again, it is going to be iterative and greedy. I'm going to start with nothing. So let this blob denote my initial matrix. All the eigenvalues are at 0. And I want to keep track of this cloud of eigenvalues, which ideally I would like for it to sort of float forward in a steady way, like in the Laguerre polynomials. So I'm going to enforce that by keeping 2 fence posts here, which I'm going to call barriers. And I'm going to maintain the invariant that these eigenvalues always lie between the barriers. All right. So initially the barriers are going to be at minus n and n. The reason for that is going to become clear. And initially my eigenvalues are all 0. And in each step I'm going to choose a vector to add from my collection, which added up to the identity, times some scaling. And this is going to cause interlacing. So it's a rank 1 update, so it's going to cause some interlacing. These eigenvalues are going to move forward. And now I want to enforce the speed of this moving forward process. And I'm going to do that by shifting the barriers. Okay? I'm going to shift the lower barrier by 1/3, so constant in every step, literally 1/3, and the upper barrier by 2 in every step. And what I'm going to do is maintain this invariant, that the eigenvalues always stay between the barriers, and the eigenvalues move forward at this, the barriers move forward at this constant speed. And notice that what's going on is sort of asymmetric, right? So when I move the lower barrier forward, I'm actually tightening a constraint. I'm saying that now my eigenvalues of my matrix need to be bigger than what they were before. So that you should think of that as pushing the spectrum forward. But if I look at the upper end, I'm actually loosening the constraint. I'm giving myself more space, right? I'm saying that I'm going to give you, slack of 2, more room for these eigenvalues to move up. And the rate at which I'm increasing the slack is actually greater than the rate at which I'm pushing the eigenvalues forward. Okay, so this is the very high-level plan of the proof. And if I can do this, then I get the following situation. So I start at 0. These guys are minus n and n. At every step, I keep the spectrum between these fence posts. And at every step, I choose some vector which allows me to maintain this invariant, to move these guys by 1/3 and by 2. And I will keep doing this for a bunch of steps, right? And what happens eventually is after 6n steps, the lower barrier is going to be at n, and the upper barrier is going to be at 13n. So I move the upper by 2 and the lower by 1/3. And then I'm going to be done. This is my 13 approximation of 6n vectors, right? So basically, I'm just keeping track of this cloud of eigenvalues by moving these barriers forward. And this is supposed to, this is supposed to emulate the behavior of what happens with these expected polynomials. Okay, so what I just told you again is just a story. There's no content here. I haven't told you why I should actually be able to do this. And so the whole content of the proof is to show that this process can be sustained with actual honest-to-God vectors that I choose at every step from my collection of vectors. And why should I even expect this to work at all? Well, the hope is that the vectors are spread out evenly in all directions. So they're decomposition of the identity, they're isotropic. So at a high level, there's no reason I should get stuck. There's no reason why I should be forced to hit one end of the spectrum more than the other end or something like that. And so everything should be sort of smooth, and this whole thing should grow at a steady rate. Okay, so as stated, this is not true. So this induction hypothesis that I was using here is that my eigenvalues are contained between these barriers. Right? So this is unfortunately not true. It's simply not true. So there are situations where you can have a matrix and the eigenvalues are contained in some bounds. And you have a set of isotropic vectors, and no vector that you add is going to allow you to move these guys by a constant. And the reason is interlacing, actually. So here's the situation. I have a matrix with all of its eigenvalues near the lower barrier. Right? So let's say I have n eigenvalues right here. Now, any vector that I add is going to, now think of the electrical repulsion model here, is going to add some charge to all of these guys. But because they're right next to each other, they're not going to move at all. Just the top one is going to shoot forward. So pretty much any vector that I add is going to have this behavior. If I have accumulation of eigenvalues near the bottom of the spectrum, any vector that I add is just going to shoot the top one and fix the bottom ones. It has to, because that's what interlacing says, right? But then I'm stuck, because then I can't move this forward. I'll have to jump over the eigenvalue. Similarly, with the top end, something very bad can happen. If I have a matrix, all of whose eigenvalues are right next to this top barrier, they're bounded by some number, then any vector that I add, the same thing is going to happen. The eigenvalues are all clustered together, all be whatever repulsion is going to happen right here. These guys are all going to get stuck because of interlacing, and one of them is going to shoot forward, and it's going to shoot forward by a lot. And there's no reason to expect that I can make this go at a small pace. So this is simply not strong enough to do the induction. So as stated, this is just not true. So what you do instead is you need to get a better way you need to basically get a stronger induction hypothesis. You need to maintain a stronger invariant, which says that this clustering of eigenvalues does not happen. So remember in the Laguerre picture, the way I drew it, these eigenvalues were sort of just, you thought of them as a cloud, like all just, sort of evenly distributed, not as like a really tight bunch of, yes?
By clustering, you mean that the eigenvalues should be far from the barriers. If they're near each other, is that okay? As long as they're
yeah. So what's bad is clustering near the barriers. So I agree, if they're all clustered in the middle, somewhere far from the barriers, that would not a priori be a problem.
Is that why you start with your lower barrier as minus n, even though
Absolutely
0 is...
right. Absolutely right, yeah. So that's a really good point. Clustering is only bad if you're near the barriers. And in the beginning, they're really clustered, right? They're all equal to 0. So that's why you start far away. Okay. Okay, so here's how you end up, here's the right thing to do. It's to use this potential function. So let's say I'm interested in the upper barrier for now. I'm interested in having my eigenvalues be less than u, which I'm going to call my upper barrier u, and also not clustered near u. That was the bad situation I wanted to avoid. So I'm going to formalize that by looking at this function trace of ui minus a inverse, right? Which is just sum of 1 over u minus lambda I. So it's sum of reciprocal distances from eigenvalues. So it's a trace of the resolvent. You may have seen this as the Steele's transform in random matrix theory. And in any case, it's sort of a familiar object from this calculation that I did with the expected characteristic polynomial. So my induction hypothesis is now going to be the following stronger statement, that the eigenvalues are less than u, and this upper potential function is bounded by 1. So the sum of reciprocal distances is bounded by 1. Now, that certainly implies that the eigenvalues are less than u, but it also implies that the largest eigenvalue must be at a distance at least 1 from u. But actually it implies something even stronger. It implies that if you have any 2 eigenvalues that are clustered, they have to be at a distance of 2. Or, you can't have 3 eigenvalues in a distance of 3. And generally you can't have k eigenvalues within a distance of k of this barrier. So it's this smooth sort of trade-off that if you have 1 eigenvalue, you can be sort of close. But if you have k eigenvalues, you better be at distance at least k. All right. And the way to think about this is that, in my physical model, I always have some electrical charges that are my eigenvalues. You should think of this as the total repulsion felt by a test charge at position u. Okay. So that's, instead of thinking of these as fence posts, you can also just think of them as test charges that tell me how far away I am. Okay, and then there's some similar thing for the lower barrier. Here I look at trace of a minus li inverse, which is the sum of reciprocal distances from the lower barrier. Again, this function blows up as you approach out. You have to pull it out. And my induction hypothesis is going to be that this lower barrier is bounded by 1 as well. Okay, so now this is what the actual proof looks like. I start off with a equal to nothing, and the initial barriers are minus n and n, and now it becomes clear why I set them to be these things. Because there are n eigenvalues, and they're all at distance n. So the potentials initially are both going to be 1. So this is what Mother was saying, that initially they're all clustered together, so I need them to be far. So I know that this is a horrible bound on 0, but if I want the stronger induction hypothesis, I actually need this. So initially I start off with minus n and n, and both the potentials are equal to 1. And now at any step, the main lemma that we prove is that suppose you have some matrix, suppose both the potentials are bounded and the spectrum is between these barriers. Then there exists a scaling of a vector taken from your original set. It becomes the identity, such that 2 things happen. Such that you can shift these barriers and the potentials do not increase. So you maintain the invariant, that this total repulsion is bounded. And once you can do this, then you can actually implement this argument. So you keep these barrier functions to keep the spectrum away from barriers, you maintain the stronger invariant, and then this actually works. And every step you can move by a third and two. Okay, so now the entire proof of the theorem is to prove this lemma, that this process can actually be sustained. And I'll sort of sketch the proof of this. So suppose I have some matrix A and its upper and lower potentials are bounded by 1. And I want to shift the lower barrier by a third, the upper one by 2, and I want to add some scaling of some vector. So the first question you might want to ask is, what vector should you add? I have many choices of vectors to add. Roughly what I want. Roughly I know what I want to do. I want to add a vector which increases the small eigenvalues and does not increase the large eigenvalues too much. But how do I formalize that? So it turns out the right question to ask is not which vector should you add, but given any particular vector, how much of it can you add? So focus on the scaling factor instead. Okay, so let's look at the upper barrier for now. Okay? So I have some matrix A, and suppose I have some vector V, and I want to add S times VB transpose. I want to add this amount of this vector, and what I would like is that after shifting the barrier from U to U prime, which is U plus 2, so this is done to create more space for this new vector, I would like that the new potential does not increase. Okay, what does that mean? Well, the upper potential of A plus SVB transpose at the shifted barrier, U prime, is literally this, trace of U prime I minus A minus SVB transpose. Right? That's just the definition. And now, we come to one of the, reasons why this function is very special. It's that there's an explicit formula for how this function changes under a rank 1 update. So the proof of it is, the proof of this is not very different from what I showed you over there, actually. But basically, there's an explicit formula called the Srivastava formula that you can derive in 2 or 3 lines. It's just linear algebra that shows that the trace of the inverse of a matrix, the trace of an inverse of a rank 1 updated matrix is equal to the trace of the inverse of the original matrix minus some ratio involving quadratic forms. So applying this, I get an explicit formula for the new value of the potential function. So the upper potential of the updated matrix at the shifted barrier is the potential of the old matrix at the shifted barrier plus this stuff, which depends on S only here. There's a 1 over S here, where S is the scaling factor. And I know exactly what I want from this. I want this to be at most whatever the potential was before. There's nothing mysterious about this. This is an explicit formula for the new potential. I want it to be at most the old potential. What is the range of feasible S that allows me to do this? Well, I just rearrange this inequality, right? And I get that this new potential at the shifted barrier, after adding S times this vector, is at most the old potential, if and only if this is true. This is literally just by rearranging what I showed you on the previous slide. Okay, now what is this saying? It's saying that I can add S times a vector V if 1 over S is at least some quadratic form of some matrix, which I'll get to in a moment, with V. Okay, so this is sort of, so first of all, this makes sense because it's a lower bound on 1 over S, which means it's an upper bound on S. So for any vector, adding more of the vector increases the eigenvalues more, right? So there should be an upper bound on how much I can add. And certainly I can always add 0 of any vector, right? Because adding 0 of any vector doesn't change the spectrum. And moving this upper barrier forward only reduces the potential, because it reduces the repulsion. Okay? So, don't look at this too much. The point is that the feasibility condition for how much of a vector I can add can be written in terms of a quadratic form in V, which is just some matrix, this thing that I'm going to call U sub A, inner product VB transpose, where the inner product is the entry-wise inner product. Okay. So now I can do the same thing for the lower barrier. It's identical proof. I get that I can add S times a vector without increasing the lower potential, if and only if some quadratic form involving this vector is at least 1 over S. Now this is the opposite kind of inequality. It says that it's an upper bound on 1 over S, so it's a lower bound on S. That also makes sense, right? Because I want to push the eigenvalues forward. What it's saying is that I need to add at least some amount of this vector V in order to achieve that. And unlike in, I mean, this is important, unlike in the case of the upper barrier, it's not the case that I can add, infinite amount of some vector and be guaranteed that I increase the eigenvectors, right? Because, for example, if I just add v that's a multiple of the top eigenvector, that's not going to touch the bottom of the spectrum at all. So it doesn't matter how much of it I add, I cannot make progress. So this formula, I mean, it's reflected in this minus sign in this formula. This is not a positive semidefinite matrix. So there are vectors for which this quantity is just negative, and no matter how much of it you add, you are not going to make progress. In any case, the feasibility condition for the lower barrier is 1 over s at most subquadratic form. So now the goal is to show that there's some scaling of some vector that allows you to do both these things at once. So I just derived conditions for how to do each one of them separately. I want to do both of them at once. And to do both of them at once, it suffices to show that there's a single vector for which this quadratic form for the upper barrier is at most the quadratic form for the lower barrier. Because if that's the case, then I can squeeze this scaling factor in between. So remember that this is what I need for the upper barrier, and this is what I need for the lower barrier. If this bound for the upper barrier is less than the bound for the lower barrier, then there's a feasible S. So, in words, what it's saying is that for every vector, there's an amount that you can add without blowing up the spectrum too much. And there's an amount that you must add in order to push the lower end of the spectrum sufficiently. And you're looking for a vector for which the amount that you must add is less than the amount that you can add. Okay. And this is reflected very sort of precisely in this inequality of quadratic forms. So now I need to show that there exists a vector for which this inequality is true. And there's no S anymore, because I'm just going to put the S in the middle. And this I'm going to show by an averaging argument. So I'm just going to sum the left-hand side and right-hand side over all my vectors B. Right? Now, this is where the sort of, very important thing happens. These expressions are linear in these outer products of V transpose, right? So if I look at the sum over all V of UA inner product of V transpose, this inner product is linear. So this is just UA inner product sum of all the possible V transpose, which is sum of V transpose, right? But now this is the only place in the proof where I use what I know about these vectors. The only thing I know about the vectors is that they add up to the identity. So the average value of this quadratic form, which measures the average somehow goodness of a vector with respect to the upper barrier, this ends up being just the inner product of this matrix with the identity, which is just a trace. Okay. Similarly, and this is this step in the proof where you really emulate the behavior of these Laguerre polynomials, and where you're able to do as well as expected polynomials, because this entire calculation is completely agnostic to what the vectors actually are. All it cares is that they add up to the identity. So, here, this is where I'm getting sort of this behavior of this balanced vector that I was dreaming about. Okay, so I need to control the trace of this matrix. I need to bound the trace of this matrix. So the trace of this matrix is equal to this, literally. It has two terms. I could spend quite a lot of time telling you what these terms mean, but let's just do the calculation for now. So the second term is actually recognizable. It's just the potential of the matrix at this shifted barrier U prime. Okay, this is at most the potential of the old matrix at U, because shifting U forward only decreases the potential. And this is at most 1 by induction. This is where I use the induction operators. So the total repulsion is bounded, so this term is bounded by 1. The first term, you'll observe that the numerator is just a derivative of the potential function with respect to this barrier at U. And the denominator is a difference between the values of the potential at U and U prime. And because it's a convex function, you can lower bound it by the change in U times the derivative, and these derivatives cancel. So the trace is now literally bounded by 1 over the upper shift plus 1. An extremely simple expression for the trace of this matrix. It doesn't depend on A, it doesn't depend on V's, doesn't depend on S, really doesn't depend on anything, except for the size of the shift. Similarly, okay, so now we proved that the average value of this UA inner product V transpose is at most 1 over the upper shift plus 1. And by a completely analogous argument, you prove that the average for the quadratic form for the lower barrier is at least 1 over the lower shift minus 1. And now it becomes clear why you set this equal to 2 and this equal to 1/3. if you set the upper shift equal to 2, then this is 3 halves, and you set this equal to 1, so this is 2. And so, therefore, the left-hand side on average is less than the right-hand side on average. So therefore, there exists a vector for which it's true. Therefore, there exists a vector such that there's a scaling that you can add. And then you iterate this process, and that proves the theorem. Okay, so basically, keeping track of this total repulsion gives you a formal way to, well, choose vectors and make precise this intuition that because they're distributed in all directions, you know, there's always some vector which hits the lower end of the spectrum enough and doesn't hit the upper end of the spectrum too much. So then that proves this theorem. And if you do everything carefully, if you fix the number of steps to dn, you get approximation factor of square d plus 1 over square d minus 1 the whole square, which are literally the extreme zeros of the Laguerre polynomial. So you actually get back exactly the bound that you got for this dream thing going on. And this corresponds to 4n over epsilon squared. And you can show that you can't actually do better. This is tight with a factor of 2. So I'll talk about this in detail tomorrow. It's not possible to beat this by a factor of more than 2. Okay, so let me just look back and sort of understand what went on here. So everything was based on this sort of central object, this potential function, which is a trace of the inverse of ui minus a. And this served two very important purposes. So one is it allows you to bound the spectrum of a matrix. So if this is bounded, it tells you that the eigenvalues are at most u and they're bounded away. And it's also, by knowing this, you can sort of know where the eigenvalues are, but the eigenvalues don't have a closed form expression, whereas this does, right? This is a very simple rational function.
Nikhil, you motivated this by saying, that having these sharp edges on a spectrum was too much, and so you wanted something that captured sort of the distance from all the eigenvalues. Yeah. And there seems to be lots of functions that would do that.
Yeah. So right. So okay. So there are several important. Okay. So I believe this is the right function. There are reasons why you can't analyze any other function. So the fact that this function varies smoothly under rank 1 updates is very important. That's the only reason we had an explicit formula for what happens to the potential when you add this rank 1 matrix. That's just a statement about the proof, right? That's not saying it's the unique function. But I think the way I see it, it really is. If you really believe that the eigenvalues are electrical charges, and that's really a good way of thinking about them, then this is sort of the only function.
So I guess the rank 1 update formula is nice, but if you just did like a continuous addition, like I just took a derivative, then it seems like you could analyze, that you could get a formula at least.
Right. If you just took a derivative, you could do anything. You could do all kinds of stuff. So yeah, you're right. It's important that you can It's important that you can analyze perturbations of this function under finite size rank 1 updates, not tending to 0. So what you're saying is true. If you could continuously add vectors, well, then you could do anything, right? Then you could just then there's no problem. Then you just move all the eigenvalues forward at the same rate.
If your potential is nice enough, then maybe the vector you choose would stay stable over a period of time.
Right. Yeah, I guess that's another way of seeing it. That the fact that this implies you can take finite step sizes sort of means that it stays stable. From a really technical point of view, any other function you try. So there are tons of functions where you can try this, and it'll work up to first order. But then you will have no way of bounding the second order terms. And this doesn't have second order terms. This gives you an explicit formula with the entire thing. And it's very special for rank 1 direction. So it's not true for higher rank. But it's a really good question. Can you find other functions that prove a theorem like this? So I think that's a really good question. Okay, so you use this to bound the eigenvalues, but it also turned out because the vectors were isotropic, they added up to the identity, the expected quadratic form with this matrix is also equal to this trace. The same trace is equal to two things, right? This is what happens whenever, in any kind of trace formula. You expand the trace in terms of eigenvalues, and here you expand it in terms of these quadratic forms. And then this being bounded serves this additional function that it tells you that there exists a good vector. And then you have this compact induction hypothesis that you can make here. Okay, so what are the themes here? Well, you should think there's another picture of eigenvalues as repelling electrical charges, which is sort of a useful thing, especially from the point of view of rank 1 updates. And I mean, okay, really the bottom line is, I mean, this is something that's been done in random matrix theory for a very long time. If you have a matrix and you care about its eigenvalues, don't try to look at the eigenvalues directly. They're sort of very non-smooth objects. Instead, look at some analytic object like Zi minus the inverse, or traceable. So it's called the result. And well, this is just another instance of turning something, like roots of like eigenvalues into some soft numbers. So there are a bunch of open questions. So currently it's super slow algorithm. It's 10 to the 4. And yeah, sort of along the lines of what James was saying, it would be really nice to have a proof of it that's motivated by something other than this expected Laguerre polynomials and basically ideas from random matrix theory. Is it possible to have a proof that's somehow based on optimization or something like that? And this is really a statement about approximating arbitrary positive semi-definite quadratic forms by sparse ones. So it already has lots of applications outside graph theory in metric embeddings and numerical linear algebra and stuff like that. So there should be more applications. Let me end by making another observation. So, the thing that motivated us to work on this or to do this was that there was no log n here, right? And now we removed the log n. But now when you're coming back to this example, there are no weights here either. So I know that I need weights in general, but for the complete graph, there are no weights in this example because I mean all the weights are the same. They're uniform weights. So you can ask, can I produce a sparse approximation of the complete graph with no weights? And currently this algorithm does not do that. It gives no control over the weights. And then there's an even other issue, which is that the right answer is 2 over epsilon squared. And we get 4n over epsilon, 4 over epsilon squared. So actually, for the complete graph, the degree that we get is off by a factor of 2. It's not exactly shown. So tomorrow I'm going to show you how to resolve both these issues, how to get 2 over epsilon squared degree unweighted approximations of the complete graph, which are also called Algorithmic graphs. And roughly the proof of it is that this stuff is not a dream. Any questions? Yeah.
So what is the actual algorithm? Because your proof is based on the problem with sigma.
Yeah, so the actual algorithm is not very hard. I mean, so the actual algorithm is, in every step we need to show that there exists a vector with some scaling so that neither potential increases, right? And that was reduced to finding a vector for which this inequality of quadratic forms holds.
Yeah.
These matrices UA and LA are very explicit matrices. So the algorithm is literally, at every step, you just literally compute these quadratic forms for every vector. There are only m vectors. And this guarantees that there exists one for which this holds. And find that one and just use that.
So yeah, just exhaustive search.
Exhaustive search, yeah.
So when you try to sparsify one edge at a time, is it possible to get any sense of what this partial graph looks like as the algorithm goes on?
Yeah, that's also a really good question. So there's, it would be great to make some statement. Like, so if you run this on the complete graph, right? We know that if you run it long enough, you get an expander. It would be really great to say something like, at time t, you have this many components that are all expanders, or something like that. And I think that's very much worth doing. The problem is we just have no global picture of what this algorithm does right now. We have no control on the weights. All we know is that the eigenvalues increase at some sort of rate. It would be great to get a better handle on what these edges actually are. And in particular, what happens when the lower barrier crosses 0, because something funny happens.
That's when you're guaranteed it's connected?
That's when you're guaranteed that it's connected, yeah. And
all right, if there are no more questions, let's thank the speakers again for the